In our last video, we were talking about the sum of the forces, the second law. And there's only two possibilities. So this is kind of from a really old physics book. So it really has a retro look to it. But I think it's good to show. So if we have the tug of war with the top people, they're not moving. There's an equal force to the left and an equal force to the right. So you see that the rag or the ribbon tied in the middle doesn't move. In that case, because it's equal, the sum of the forces is 0. Now, in this case, in the bottom situation, the one team is obviously winning. We would say then the sum of the forces equals ma, because overall there'd be an acceleration. The rope and the other team would move that way over to the left. So that's the second law. And the unit of force is named for Isaac Newton. It's called the Newton. So we can see that it comes from the formula. Force equals ma. Well, mass we measure in kilograms, and acceleration meters per second squared. So 1 kilogram meter per second squared is a Newton. Now, a Newton, what that means is a Newton will accelerate a 1 kilogram object from rest to 1 meter per second, can get it up to a speed of 1 meter per second in 1 second. That's hard for us to imagine. That it's very theoretical, and well, what does that mean? To give you an idea of a 1 Newton force, if you take your two pinkies, and I'm not going to spend a lot of time drawing this, but if you take your two pinkies and put one on top of the other and push down a little bit. Just with the pinkies. Don't move your whole arm. Just move with your pinkies. That force is roughly a Newton. Somewhere in that ballpark is roughly a Newton. Maybe I can make it a little more realistic. Put a thumbnail and fingernail on there. So a Newton is a kilogram meter per second squared. And of course, what's physics without some math? So a 60 kilogram bike and rider, that's not unreasonable maybe for a fairly light high school student or a lighter high school student. They're riding and they accelerate at 0.5 meters per second squared. So they are speeding up. So we can ask, well, how much extra force did the legs provide? So we're accelerating, so the sum of the forces is ma. Now, they don't tell us anything about air drag or friction from the wheel. We're not going to concern ourselves with that just yet. So it's really easy. We just do ma, 60 kilograms times 0.5 meters per second squared. And we can easily see that that's about 30 newtons. So about 30 times what you're exerting with your pinky. Now let's say we have a watermelon. Oops, I don't have the math on there. Now we know the force to accelerate the watermelon. I don't know, maybe we're throwing it or sliding it down a bowling alley or something fun like that. So the sum of the forces is ma. Now since we're only working with one force, I'm going to leave out the sum just to make life easier. Let's see what variable we want. We want the mass. And you know me, I prefer to do the algebra first, and I hope you get in that habit. So I'm going to divide over the A. So the force was 5 newtons, and the acceleration was 2.5 meters per second squared. Now remember that a newton is a kilogram meter per second squared. So if we can look, we see that the kilogram meter per second squared, or the meter per second squared cancels, and it leaves us with kilograms. Which is 2 kilograms. Oh, I didn't watch my significant figures there. We really should do that. Well, that's about a 4.5 pound watermelon. That's not unreasonable for the size of a watermelon. So this is a really simple formula. And I know what you're thinking, well, you're going to make it more complicated. Yeah, let's see how that's going to happen. So let's have this bowling ball. The bowling ball is going to start at rest. Because if we're at the bowling alley, we just pick up the bowling ball and it's not moving. And we want to really accelerate that bowling ball, hopefully get the strike to 20 meters per second. So we've got a V initial and a V final. Now we don't know how long or how far we went with the bowling ball, but we do know that the time was 2 seconds. All right, well, just using kinematics, just using the definition of acceleration, we could find, well, at least what the acceleration is. And we like problems where they start from rest because then the initial is 0. So the acceleration is just 20 meters per second over 2 seconds, which is 10 meters per second squared. Now to get the force, and it's really only one force, so we'll just do F equals ma. It's easy to substitute. It was a 5-kilogram bowling ball. That's a pretty heavy ball. That's probably like a 12-pound bowling ball. And we want to accelerate it at 10 meters per second squared. So 5 times 10, so that's 50 newtons. And as always, we circle our answer. Now, one more for today. Let's do the force required to stop a car. Of course, if it's going to be a car, it may as well be the Batmobile. So the V initial is 27.8 meters per second. That's 100 kilometers per hour. But Batman needs to stop, so he needs his final speed to be 0 meters per second. And it takes 55 meters. We're going to again go back to kinematics, but we're going to use the time-independent equation. In this situation, V final is 0. So we've got to do negative V initial squared over 2 times the distance. Negative 27.8 squared over 2 times 55.0. That's only going to get us the acceleration. It's not going to get us our final answer. So the acceleration is negative 7.03 meters per second squared. And it's perfectly fine that it's negative. In fact, it has to be negative because the vehicle is decelerating. So let's see. So sum of forces is ma. And it says net force. That just means overall. So let's see. The Batmobile is 1,500 kilograms. Acceleration is negative 7.03 meters per second squared. So that works out to negative 10,500 kilogram meter per second squared, which is negative 10,500 newtons.